let's say that we're going to, well, here's the way that we'll normally approach it. We'll first find the CNs. So let's say there are three CNs. Let's say at 1, at 3, and at 5. All right. So let's say we have CNs here. CN, CN, CN. All right. Let's say we have a function with 3 critical numbers. Let's say domain's all reals, just for the heck of it. All right. Now, it would help to know the derivative. And it would help to know the sign of the derivative, right? It would help a lot if we knew the sign of the derivative for various values of x. Okay, so let's take a look at f prime. Oh, this is yellow, actually. Okay, so let's say that we analyze f prime. We find it's negative here. It's 0 at this Cn. Let's say it's positive here. It's 0 here. Negative here. 0 here. And hey, let's say it's negative here. Okay. Remember, you don't have to change sign to the 0. Remember that. You don't have to change sign to the 0. Okay. And then what might be some strategies then? Well, it might help to know what the points are at 1, 3, and 5, right? So we plug these numbers into Big Daddy F, and we find 3 points. Okay. This point here, this point here, and this point here. Okay, so I'll often ask for that on exams. I want you to identify the points at critical numbers. Now, are some of these points interesting? And if so, why are they interesting? Okay, because why do we care about critical numbers? Because that's where we look for what? What kinds of points? Local what? Local maximum endpoints, right? Local extrema. Okay, but which ones are they? Are they local maxima, local minima, or maybe neither? Remember, there might be neither. Well, you know what? If we have all this information, we already have an idea of what this graph might be looking like, right? Because look, if f prime is negative, which way will the tangent lines be sloping? Downward, right? They're falling. We have falling tangent lines. So, assuming that, you know, by the way, notice here, I'm assuming that f prime is defined everywhere, right? What's happening to the graph? Is it going up, going down? What's it doing? It's going down. It's going down, right? Because if the derivative is negative, right, and the tangent line is sloping downward, that means the graph has to be going down. That means that the function is decreasing. Okay, so that's a key principle there. So, all right. Likewise, over here, okay, at this Cn, we see that f prime is 0. We have a horizontal tangent line. Okay, so it's possible that we bounce off. Do we bounce off? Do we bounce off, or do we go on our merry way? We bounce, right? Because f now has to be increasing, right? F prime is positive. That means that the tangent lines are doing what? They're rising, right? They're sloping upwards, right? We slope here is positive, right? All these slopes here are going to be positive. Right. Over here, okay, f prime is 0. Again, what kind of tangent line do we have when f prime is 0? Horizontal. Remember back in chapter 3, we found a bunch of these guys, right? We often look for horizontal tangent lines. Okay, well, f prime now goes to negative. That means that the graph is turning around. We have a turning point here, okay? And we go over to this point here. But now, look here. F prime is negative here. Also, it's negative here. Are we going to bounce off and go up, or do we just go on our way here? We're going to go on our way. Yeah, it's like a pit stop, right? We just go on our way here, all right? Because we need the slopes here to be negative, the graph is still falling. All right. So, what can the derivative, in particular the sign of the derivative, tell us about whether the function is increasing or decreasing? All right. Well, let's look at a couple of examples, right? I'm claiming here that f prime is positive between 1 and 3. All right. So, f prime, all right, is positive. I might just put a big old plus sign there, right? F prime is positive on the open interval from 1 to 3. Okay. Therefore, I can say that f is, okay, well, what's f doing? Between 1 and 3, is f increasing or decreasing? It's increasing, right? So I can say that f is increasing. Okay, from now on, I'm just going to put a big arrow going like that. That doesn't imply linearity or anything, but it implies that the function is increasing. The graph is going up, right? And usually we assume continuity, at least. At the very least, we tend to assume continuity if we're talking about a function being increasing. We're not just looking at dots, right? Okay, the function is increasing, and you might say, well, can we say it's increasing on the open interval from 1 to 3? Well, sure, but I claim that in this example, I can actually say that f is increasing on the closed interval from 1 to 3. Now you might ask, well, how's that legal? Why can I do that? Because you would think f is continuous on the closed interval from 1 to 3. So for that reason, I can still I can go to brackets here. Okay, so this is by continuity of f on the closed interval. Let me take you back to pre-calculus. I know many of you would be eager to go back to pre-calculus, but back in pre-calculus, what does it mean for a function to be increasing on an interval, whether it's open or closed? Well, if you take the interval, right, take any two distinct points on the interval, the guy on the right is higher than the guy on the left, right? So you can define the property of being increasing on an interval back in pre-calculus. You didn't need calculus, right? Well, you agree that if I extend the graph to include this endpoint here and that endpoint there, that property still holds, right? If I consider the entire piece from this point to this point, anytime you take two distinct points, maybe even these guys, okay, the guy on the right is going to be higher than the guy on the left, right? So the increasing property holds on that interval. Now remember, folks, we say that f is increasing on an interval. We technically don't say it's increasing at a number. So we don't say that f is increasing at 2. Now, we might say that informally, but it would be informal, okay? Technically, a function increases on an interval. You need comparisons, right? Okay. Now, if you put open parentheses instead of brackets, again, will I be profoundly offended? No. But if we have the right to put brackets, then we do. We try to get the most powerful statement possible. Okay. And again, we can do this by continuity. Okay, we can do this by continuity. Obviously, if we had like holes or something like that going on, then maybe we couldn't do that. But if you have continuity on that closed interval, we can put brackets. And I talked way too long about a very subtle issue. But any questions? Any questions? You can put parentheses line. By the way, know the difference between an interval and a point. By the way, when you use parentheses. Okay. It's all context. All right, so we can say that. Okay. Now, what else can we say? Well, let's take the interval from, let's say 3 to 5. All right. F prime is negative, big old negative sign, on the open interval from 3 to 5. Okay. Well, from here, we can say that f is decreasing. Henceforth, I'll use this symbol. Again, don't think linear, but it is decreasing. All right. F is decreasing on. And again, by a continuity argument, I can say brackets 3, 5. Okay, f is decreasing on this interval. By continuity of the function, right now, I'm just being kind of conservative right now. I'm just going to say that for now. But you would be right that the function would be decreasing off as x approaches infinity. Okay. And the fact that it's 0 there doesn't hurt that fact. Okay. But questions? Questions? We're being a bit more precise about what it means for a function to be increasing versus decreasing.
Would it also be true if we say that f is decreasing from negative infinity all the way to 1?
To 1, that's fine. In fact, that's implied. Right. If the graph is extending as expected, sure. Okay. But I want to point out, this is why we care about the sign of the derivative, because if we know about the sign of the derivative, then we can make comments about where f is increasing versus decreasing. And you agree that if we can figure out where the function is increasing and where it's decreasing, we can figure out where a graph is turning around, right? And that's something we couldn't do in pre-calc. That's something that we do in calculus. Okay, where are the turning points? And what kinds of turning points are they? Are they local max points or local midpoints? Maybe some of those guys are absolute. All right, questions so far? Questions? You agree the sign of the derivative can be very important when it comes to classifying. Hence, the first derivative test. We can use the first derivative. In particular, it's, what's the key part of it? It's what? It's sign. I don't care so much that it's positive 10 or positive 12. I care about sign, right? Is it positive? Is it 0? Is it negative? All right. Okay. Now, there are various ways you can do these kinds of analyses. All right. One way you can do it is by what we call the test value idea. Okay. And the test value idea is based on a fairly basic principle of functions. All right. Question. Where are the only places that f prime, remember, we care about the sign of f prime. Where are the only places that f prime could change sign? Not must, could. Where are the only places that f prime could change sign? All right. For example, if we're dealing with polynomials, okay, f is polynomial, therefore all its derivatives are polynomial. Where are the only places that a polynomial could change sign? At its what? What's that Z word? Zeros. Okay. So, where are the places? At its zeros. Okay, meaning the zeros of f prime. At its zeros of f prime. Okay. At its zeros. Or, well, what if it's not polynomial? Where else? Where else could we have a situation where f prime is suddenly changing sign? Or where f prime loses what property? What are properties of functions that we like? Well, that's defined, and furthermore, what else? That it's continuous. See, if f prime loses continuity, then anything can happen, right? Okay. Or where f prime is discontinuous. Okay. Now you might go, well, that sounds awfully precise, this idea that f prime is discontinuous. Do you know the most frequent time when this happens? When f is undefined. That's the most common time when this problem appears. Okay. In particular, especially, when f is undefined. Okay. So those are especially places where f prime could change sign over a place where f is undefined. Okay. Although, in general, whenever f prime is discontinuous, then you have the potential of changing sign. Right. Especially when f and f prime. Okay. Especially when f, or for that matter, f prime. Basically when something's undefined, f or f prime, when something's undefined. Okay. Okay. Questions? Questions? Okay, questions? All right. So how can we apply this idea back to our previous example? All right. So here's the x-axis, or whatever, t or whatever, right? Theta. But here, let's say it's x. Okay. Now, first of critical numbers, right? Because if, oh, well, critical numbers, where are we going to put our fence posts? All right. Place fence posts, okay, at critical numbers, okay, and anywhere else where f prime is discontinuous. Okay, now why do we put fence posts at the critical numbers? All right, well, what's a critical number? It's a number in the domain of Big Daddy F, where f prime is what or what? Zero or D&E, right? Okay. So fence posts at C ends and where f prime is discontinuous. Okay. Now that seems too precise. I'm going to add something here. If that seems too precise, bear in mind that f prime is discontinuous whenever Big Daddy F is discontinuous. And what's an example of being discontinuous? Where you're undefined, right? So basically, if f or f prime is messed up, bottom line, if f or f prime is messed up, you got to put a fence post in, all right? In addition to the critical numbers. All right. Now here, in the example I showed you earlier, I assumed that we had 3 critical numbers and that these guys were cool, okay? Like we had polynomials, all right? So I wasn't so worried about these cases. We're focused more on the fence posts that were at CNs. So in the example I showed you earlier, okay, let's just say we were dealing with polynomials. We had 3 critical numbers, okay? 1, 3, and 5. So we have a Cn here, a Cn here, and a Cn here. Okay. Now, I'm going to put f prime, okay, up here. This time I'll put this above the axis instead of below like last time. All right. Let's talk about this. Now, I just proposed to you that since we are dealing with a polynomial, the critical numbers have to be where f prime is 0, specifically. Although in general, you could have D&E for a more general example. But let's say that f prime is 0 at our CNs, like for a polynomial. Okay, now, fine. We know where f prime is 0, and we know f prime is defined everywhere because it's polynomial. Okay, now the question is, how can I figure out the sign of f prime everywhere? Well, remember the principle, right? The fence posts are the only places where f prime can change sign. Okay, so again, these places I'm going to call fence posts. Okay, they correspond to markers on the x-axis where f prime could be changing sign. Okay. Here we only have 3 fence posts. They're all at where? At the what? At the critical numbers. That's why we care about critical numbers. Okay. And also domain issues in general, right? Bear in mind, if Big Daddy F is undefined, we don't have a critical number, but still, we care, right? That's a place where we might be having something kind of weird happening. All right. Now, here's the deal. I want to know the sign of f prime in that left window. All right? Now, I could test a value. Well, give me a number less than 1. 0. Okay? Or sometimes it's easier to use negative a million. Sometimes testing a ridiculous number is even more helpful and quicker. All right? But we can test 0. And let's say that we find that f prime of 0 is negative. Now, here's my claim. You agree that if f prime is negative here, it's negative all throughout this first window to the left of 1. It's negative here, 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 everywhere to the left. Do you all agree with that?
Yes.
Why? Yeah, why? Because if we change sign, we'd have another fence post, right? Either a CN or something's messed up, right? Do you all agree with that? If we test a value in here, okay, we find the sign, that sign applies in the entire window because you have no other opportunity to change sign for f prime anywhere else in here. You agree? Well, come on. What's a logical choice for a test value in here? 2. Okay? And, I don't know, look at my example. Let's say it's positive, right? You find f prime at 2 is positive. That means it's also positive here, and here, and here, and here. It's positive all throughout that open interval from 1 to 3. Remember, it is 0 at the endpoints here. 1 to 3. Okay. And then, again, over here, test 4, right? We find that f prime is negative in this entire window. Over here, at f prime of 6, or for that matter, a million. Like I said, sometimes a ridiculous value is easier. Okay? We find that f prime is negative once again. And by the way, that's okay. Remember, I say here, the fence posts are the only places where f prime could change sign. I didn't say must. Could change sign. Right? Okay. So, identify the fence posts. That's why we care about critical numbers. Bear in mind, however, we do care where f and f prime are messed up. Okay. Before I go on, what do I mean by messed up? Basic example. Example. let's say f of x equals 1 over x squared. Okay? F of x is 1 over x squared. All right. What's the derivative? Well, the derivative of x to the negative 2 is what? Negative 2x to the negative 3, right? Negative 2 over x cubed. All right? So if you do your fence post, right? Okay. Well, look here. F prime is never 0, right? That's never 0. When this is undefined, that's undefined. There are no critical numbers. There are no critical numbers. But wait a minute. There is a fence post. Where's our fence post? X equals 0, right? Why? Because, well, for one thing, F is undefined there, right? That's messed up. F itself is D and E. F does not exist. All right? And in fact, if you look at F prime, what happens with F prime? Okay, if you look at F prime is positive over here, negative over here. Okay, obviously it's D and E here. Bear in mind, if F is D and E, so is F prime. Okay, if you look at the whole chain, well, the whole sequence, F, F prime, F double prime, as soon as one guy goes to D and E, like dominoes, so do all the higher order derivatives. Okay, if F is D and E, so do all the first, second, third, row D and E. Okay, by the way, what is the graph of y equals 1 over x squared? It's even, always positive, where it's not 0. Remember this? Volcano. Volcano. See here? The derivative, see here? Hey, look at this. F prime is positive. On an interval where F prime is positive, okay, and I know that this is technically open, right, but where F prime is positive, F has to be doing what? F has to be increasing. You agree? F is increasing. So, to the right of 0. When F prime is negative, what's happening to F? Decreasing. F is decreasing. Okay. So this is why, we also have to put fence posts. By the way, you might want to jot this down. I should have said this before. I didn't put this example in my notes. You might want to jot this down because it's an example where we have a fence post here where F prime changes in sign, but it's not a CN. It's a place where everything's messed up. Okay, so I should have mentioned this. This is not in my written notes. You might want to jot this down as an example of a fence post that's not a CN. Okay? There are no CNs, but that is a fence post. F prime is a changing sign. Bear in mind there are no local extrema here.
If we don't know what the function is or what the graph looks like, and all we have is this fence post, like number line kind of deal, can we say whether 0 is a whole or an asymptote?
Well, I'd have to give you some more information about the function.
Okay.
Now, here's what I could do. If I give you information about signs, for example, you can make determinations about whether you have local maximum or local minimum. And on homework, I do have that. Here's some function. I don't tell you much about it. Okay, I don't tell you it's x to the whatever. I don't give you the rule, but I'll tell you, hey, here are the critical. It's differentiable everywhere. Here are the critical numbers. Okay, here's the sign of f prime. Here, right? Do we have a local max or local min at this critical number? That's fair. Something like that would be fair, where I don't give you the rule, but I give you some specifications. Yeah. But then you'd be applying the first DT, which we're going to talk about. But questions? Put fence posts at CNs, and wherever F or F prime is messed up, because of course F prime can change sign around like a VA or something. Right? Okay. For a polynomial, you have no VA. All right. We love polynomials. There are no special cases. All right. Now, in my notes, I do an example with a parabola. It's super boring and easy. That's a waste of time. You can read that. I'm going to talk right now about the first DT. What is the first derivative test? What is the first derivative test? Okay. Now, folks, I'm not going to write this the way a textbook could write it. I'm going to do it by picture. The first derivative test is really kind of common sense. It's a matter of can you draw the pictures out. All right. Now, first of all, what is the purpose of this? The purpose is to classify a point at a critical number. All right. So specifically to classify points at critical numbers, you don't have a critical number, it can't be a local max or min, right? Okay, it's to classify a point at a critical number as a local max point, a local min point, or neither. It doesn't have to be either, right? Like y equals x cubed, right? Or the point at 5, right? Or neither. Okay. By the way, when we get to the second derivative test, it's going to have the same purpose, although it cannot identify these cases, or neither ones. All right. First derivative test. Really, if you understand the principles up to now, it's really common sense. Just draw the arrows, draw the picture. All right. Now again, folks, and Swakowski doesn't do this, but I do make this assumption, okay? I say that in order to have a local maximum midpoint, you have to have continuity. Okay, I don't think Swakowski officially says that, but I say you need continuity. All right, okay, so assume f is continuous at a critical number c. All right? And of course, if you have several critical numbers, then you can analyze them separately. But let's say that we have a critical number, c, and f is continuous there. Okay, with polynomials, for example, that's never a problem. All right. Okay. Okay, so case number 1. Okay, I'm going to do it by picture. It's very boring when you see it written out. Let's do it by picture. All right. X-axis, right? So here's our critical number, c. Again, this has to be a Cn. You can't have local extrema at non-Cns. All right. Now, if f prime, all right, if f prime is changing from positive to negative around a critical number, all right, well, let's use our common sense. What is f doing? So what's f doing over here? If f prime is positive, what's f doing? Increasing, okay? By the way, the word association works here. Okay, I think word association. If f prime is positive, f is increasing. They go together, right? Over here, f prime. Oh, and by the way, folks, this is on some small neighborhood of c. Okay, so there are no other critical numbers here. We're zooming in very close to c, right? This is all very close to c. There are no other critical numbers in sight. Okay. If f prime is negative, at least temporarily, what's f doing? Decreasing. And again, we're assuming continuity here, remember? We're assuming continuity at the critical number. Okay, that's a nice thing to have. All right. Well, you can draw a picture. It might not be this nice, but look. Graph go up. Maybe there's a horizontal tangent line. Okay. Graph go down. All right. Well, come on. What kind of point do we have up there? It's a local max point. So if this all happens, we have a local max point where? At C. And how do you find the y-coordinate? Take C and plug it into Big Daddy f of C. Remember, plug into f of C, not f prime of C. I mean, what will f prime of C be? It'll be 0 in this example, right? Okay. So remember, Big Daddy f gives you the y-coordinate. Okay, f prime just checks at 0 in this case. Although, it doesn't have to be 0. Remember, you can have a critical number where f prime could be, maybe not 0, but it could be what? F prime could be what in a critical number? It could also be what? D and E. Okay, well, what's the example of that? All right. Again, let's say f prime, okay, again, is going from positive to negative. Let's say this time, f prime is D and E at C. Maybe something like this. What kind of point is this? Well, it's a local max point again. Right. Again, we have a local max point. What's that other word we have called? Corner. Okay. Or you can have a cusp. Right? You can have a cusp also. That's also where you lose differentiability. Right? So bear in mind, as long as we have continuity, and continuity implies you define there, right? As long as you have continuity, look, if the derivative is positive to your left, negative to your right, we have a local max point there. I don't really care right now whether it's a nice horizontal tangent line there, or if it's a corner or a cusp. I don't really care. The designation of a local max point does not care. All right? Look, we have continuity at C. F prime is positive to your left, negative to your right, local max point. Period. Any questions? Any questions? Here, F prime is 0, but who cares? Okay, except for actual graphic purposes. All right. Moving on.
And with that,
Yeah.
prime is meaning.
That just means that, you know, we really don't care if it's 0 D. Look, by definition of a critical number, f prime at C is either 0 D and E. But as far as the designation of a local max point goes, we don't care if it's 0 D and E. We do assume continuity. Okay, which means you're defined, by the way, right? But we assume continuity. Hey, f prime is positive to your left, negative to your right, local max point. You apply the first DT. Like I said, folks, it's common sense. I mean, you're going to be applying the first DT. You won't even be knowing. You don't even know it because you're just drawing the picture. You just use your common sense. Just draw the little picture out. And it's okay if this isn't actually the graph, right? Just draw a little picture out. And you can figure out it's a local max. All right. Case 2 is very obvious. In fact, I'll just do the 0 case here. Right? Case 2 is obvious. All right. X, let's say. All right. If f prime. Okay. Okay. Around the critical number, on a small neighborhood of the critical number. Let's say it goes from negative to positive. All right. And I don't care if it's 0 D and E here. Again, we're assuming this is Cn. Where we have continuity. Okay? Well, what do we know about Big Daddy F? When f prime is negative, what's f doing? Decreasing. When f prime is positive, what's f doing? Increasing. We're assuming continuity here, right? Graph go down. Okay, maybe we have a horizontal tangent line. Could be a corner. All right. Graph go up. All right. What kind of point do we have there? Local minimum point. Yeah. We have a local midpoint at C, f of C. So, you know, we have a Cn and continuity at C, right? If f prime is negative to your left, positive to your right, I don't even care if f prime is 0 D and E here, okay, versus D and E. You know, we're going to have a local midpoint. Questions? Issue 3. So what do we have neither? If the sign of f prime, what? It's the same. Okay. All right. So very quickly, I'll draw that out. You can figure that out. Okay. So x-axis, Cn, and continuity at C. If f prime, let's say, is positive, positive. All right. That means that f is going up and going up. All right. So that's like x cubed, right? Okay. So it goes like this. Graph go up. Maybe we have a horizontal tangent line or a corner or something, right? Okay, graph go up. Okay, so we have neither. Likewise, for the opposite of x cubed, for example, x-axis, Cn, continuity. If f prime, negative here, going down, down, like Megan Fox career, going down, down. All right. Okay. So graph go down, maybe a horizontal tangent line, whatever. Graph keep going down. All right. I don't think you can have a cusp, but you can have a corner. Yeah, you might have a corner there. All right. I think you have neither. So that, ladies and gentlemen, is the first DT in pictures. Again, just by doing some basic sketches, or just tracing your mind, you know, it's really common sense. Right? Questions? Just working with the sign of f prime around a critical number, immediately around a critical number, so that there are no other fence posts in sight. I should have said no other fence posts in sight. Of course, if you have other fence posts, you can have other behaviors. Okay. Are we ready for our first Big Daddy? Our first big example? All right.
Do this.
All right. Examples. F of x equals. Okay, you know about all polynomials up through quadratics. Cubics we don't know as well. Although from pre-calc we know a lot of them. All right, 2x cubed minus 9x squared minus 24x. All right. Again, here's some sample questions I might ask you, okay? Well, I could ask you, where is this function increasing and where is it decreasing? So I could ask you, find intervals of increase and decrease. Okay, so we can do that. Also, now, what were questions that we couldn't answer so easily back in pre-calc? Finding the local extrema, meaning min and max, right? Find local extrema. Okay, find local extrema. Question. And if you know your pre-calc, you should know this. When we graph this, will this graph have absolute extrema?
No.
No. What's the graph of this?
Same.
Yes, a rising snake. So it's not going to have a highest point or lowest point, unless you restrict it to me. But all reals? No. There is no highest point. There is no lowest point. Okay, so rising snake. However, we're wondering, this could have turning points. Not necessarily, but it could have turning points. And we'd like to know where they are. And in pre-calc, you might not have been able to find them. All right. Okay. Okay, so let's do this. Okay, let's find f prime of x. All right, so let's find the derivative. First derivative. Well, turn by turn. What's the derivative of this guy? 2x cubed. What is that derivative? 6x squared. All right. Then negative 9x squared goes to negative 18x. And then negative 24x goes to negative 24. Okay, now I want to make a comment here. All right. Theoretically, it is important. F and f prime. You agree, these guys are continuous everywhere. Right? They're good everywhere. F and f prime are defined and continuous everywhere on the reals. Okay. That's good to know. That means that our fence posts, okay, when we look at f prime, our fence posts will only be at the where? At the CNs, critical numbers. There are no other weird fence posts. Because that guy's polynomials, come on, they're good everywhere. Okay, so there's no 1 over x, there's not 1 over x squared, for example. Alright. The CNs are the only places where this thing could change something. Okay, well, let's do that. Let's find the CNs. Okay, again, these will be our only fence posts. Sorry. Let's find the CNs. Now, what's a CN? It's a number in the domain of Big Daddy F. Well, F is continuous, therefore defined everywhere, right? Where F prime is what or what? 0 or DNE, not DNE here, right? So, 0. Okay, small f prime of x equals 0. Again, the DNE case doesn't apply here. So, find where the derivative is 0. All right. For good measure, I'll write this out. Although you might want to factor directly, but I'll write this out. Okay, let's factor. And you know what? I like retaining f prime of x over here. I don't like dividing on both sides, especially dividing by a negative number. I really don't like dividing by a negative number because then that can really blow your sign analysis. So I say keep factoring. Avoid dividing. Okay, avoid dividing. Factor. Factor. So that we retain a form for f prime of x on the left side. Again, if you multiply or divide both sides by a negative number, you're destroying your sign analysis. Potentially. All right. Okay. Okay, so we factor out a 6. That's pretty safe. You could have divided. Well, still, it's safe to just keep the 6 there. Okay, although it is positive. All right. Positive 6. And then we have x squared minus 3x minus 4 equals 0. I like the fact that this is f prime of x. Okay. Although the 6 is fairly safe, but still, I like having f prime of x over here. We can factor this over the integers. Okay. It goes x minus 4 and x plus 1. Okay. Brush up on your factoring skills. You could use a QF. All right. This works out pretty nicely. All right. So we're getting x equals, in order, x equals negative 1, or x equals 4. All right, those are the two zeros of f prime of x, it appears. All right. Yeah, go ahead.
0 would be one because you can factor out an x, and there's no x attached to that 6, right?
Okay, right. Now, you have a good point. If this were like x cubed and x squared and x, we factor out an x, 0 would be a 0. But here, 0 is not a 0. So be aware of when 0 is a 0 and when it's not. If x is a factor, right, then 0 is a 0. But you're right, a lot of people, that's a very common mistake actually. People think that 0 is a 0 when it's not, okay, or they don't realize it is when it is. So be careful about 0 itself. Right. But you agree here, -1 and 4, these are the only zeros for f prime of x. And let's remind ourselves, yeah, they are in the domain of Big Daddy F, which was all reals. Now again, for a polynomial, you don't really need that check, but you know what, it's a good habit to get into, right? Because later on, what if you're not dealing with a polynomial, you might want to double check, hey, wait a minute, are these guys in the domain of F? If you're not in the domain of Big Daddy F, you gotta go, right? Go away. But these are good, which means that these are our what? These are critical numbers, -1 and 4. Okay, these are all of our critical numbers. You all agree? These are all of our critical numbers. They're the only numbers in the domain of Big Daddy F where f prime is 0. Again, the t&e case did not apply here. Questions? That's a start, right? Okay, and these are the fence posts, right? Polynomials, they can, polynomials have the property that f prime can only change sign at the CX. All right. So, x-axis. So all that theorizing I was doing before, this is more concrete now. We only have two fence posts. One at -1, one at 4. And I know that normally for critical numbers I like to indicate 0. I dispense with that here, because that can be confusing. So I'm not going to put a 0 there. All right. We have only two fence posts. There are no other places where these guys are messed up. Okay, so these are the only fence posts. Okay. And there are various ways that we can do the sign analysis. All right. So what's the deal with f prime? We know he's 0 here and 0 here. Okay. There are various ways you can do the sign analysis. Now, you can do it any which way you want, but the bottom line is that I need to see this number line with the appropriate signs up here. But you can arrive at them any way you want. Okay. You can even do them mentally. But as part of your work, I want to see the sign chart there. Okay. Get those signs any way you need to. Show whatever work you have to, but I need that sign chart, okay? Remember that. I hate taking off points when people forget that thing, but you need that thing. Okay, show me that sign chart. Okay, what's one way you can do it? I just mentioned the test value method. All right. Now, I don't want to... Okay, well, I will do this. I will do this. Okay, so I'm going to mark this up, and then I'll clean it up later. But, okay, let's do this. Here's f prime of x over here. Remember, this is f prime of x. I didn't mess with it. I like factoring, not dividing. Okay. So remember, what is f prime of x? F prime of x is, okay, well, it's 6. All right, times the factor x minus 4 times the factor x plus 1. All right. Do you agree that if I know the signs of all three factors at any moment, I know the sign of the product? Right? That's why we like to factor. That's one of the reasons why we love factoring. Because if we know the signs of the factors, we know the sign of the product. That's not true for sums. If I tell you that this is a positive number, and this is a negative number, do you know the sign of the sum?
No.
Not now. But you do know the sign of the product, right? Okay, negative. We like factoring. That helps us with sign analysis. All right. Well, give me a number less than -1.
-1 million.
-2 or -1 million. No kidding. -1 million. All right. Let's try -2. All right. F prime at -2. Bottom line, I don't care so much about the actual number. I care about the what? The sign. 6 is always positive. Okay. Still, for honesty, I like to keep it in here though. Okay. 6 is always positive. Plug in -2. Bottom line, this guy's negative. Plug in -2. Bottom line, this guy's negative. Now, one advantage to -1 million is that sometimes, you know, you get a mind blur and you go, wait, a -2 and a +1. What if you put -1 million? Oh yeah, positive, negative, negative. That's very easy. Okay. What's a positive times a negative times a negative? That's a positive. Now, remember what we said before, if f prime is positive here, it's positive everywhere in here. You agree? Right? Because there are no other fence posts out there. The fence posts are the only places where f prime can change sign. Here, that means CX. All right. And then we can continue on. F prime of 0. Actually, you know what? For f prime of 0, it might be easier to look at the expanded form, descending powers. Plug in 0. What do you get? -24, which is negative. Yeah. -24, which is negative. Okay, that's even faster than going through this. Well, here's 0. We know it's negative here. It's negative all throughout the middle window. Finally, hey, let's do f prime of 1 million. Why not? does not have to be the scale, okay? Not the scale, but a million is way out there, all right? Bottom line, plug in a million, positive, 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 that's positive. Positive all throughout the right window. Do you agree that if I give you any real value for x, you can tell me the sign of f prime of x? You agree, right? Okay. Any questions about that? Any questions? So on the test, and you can do this mentally if you wanted to, but on the test, what do I need to see? I need to see that sign chart. I at least need to see this. X, negative 1, positive 4. I need to see this. F prime is positive here, 0 here, negative here, 0 here, positive here. Okay, so I need to see that, get that any way you need to. You might ask, well, how can I do this without that kind of factoring analysis? Well, actually, the factoring here helps. Let's say you don't want to do test value, right? What if you don't want to do the test value? All right. Here's one thing you could do. All right. So this, if you feel really comfortable with polynomial theory, you can do it this way. You don't even have to test values. All right. F prime of x is a quadratic with a leading coefficient. How would you graph this guy? Y equals f prime of x. Quadratic with a positive leading coefficient. A parabola opening up, a bowl opening up. Okay? All right. Which means that it's got to be positive out here and positive out here. Right? Look at these factors. Right? The zeros are at negative 1 and positive 4. The corresponding factors have odd exponents. They have odd multiplicities, 1 in each case. That means that the graph is cutting. Positive cuts to negative, cuts back to positive. Okay, you might remember that whole cutting and bouncing thing from polynomial analysis. Okay, again, whatever it takes though. Positive, negative, positive. Right. Questions? Questions? Right. Whatever it takes. All right, that's part of your work. Any questions so far? Folks, we know the sign of f prime everywhere, right? That helps a lot. We know the sign of f prime everywhere. We know how this guy's moving. We know how Big Daddy F is moving. All right, let's talk about Big Daddy F. When f prime is positive, technically I'm an opening, but when f prime is positive, what's Big Daddy F doing? Increasing. Then there's things kind of leveling off, right? Okay. When f prime is negative, what's f doing? Decreasing, leveling off, as opposed to a quarter of us. F prime is positive, f is increasing. All right. By the way, at this point, we can answer part A. Remember, I could ask, what are the intervals of increase and decrease? We can answer part A now. Okay, so the answer to part A, all right, f is, let's see, increasing on, okay, well, negative infinity, comma, it's increasing up to negative 1. We have the right to put the bracket by continuity, by right-hand continuity. No, left-hand continuity at negative 1. This way, left-hand continuity at negative 1. Okay, f is decreasing on close brackets, negative 1 to 4. Okay. Again, if you put parentheses, that's fine, but brackets are more ambitious. We can do that by continuity. All right. And finally, f is increasing on that last window, right? Bracket 4, comma, infinity. All right. I used to put the union symbol and connect these, but that's kind of dangerous because that might imply that these points are higher than those points, and we're not necessarily guaranteed that. So I think it's okay to just do it like that. So f is increasing on that left window. F is decreasing on the middle window. F is increasing on the right window. All right. Questions? Yeah.
For the test, for the sign chart, do you want to see f prime and f on it? Or just
F prime sufficient. Okay. Yeah. But I think F will help you. Okay. Questions? Because basically you're enacting, applying the first derivative test right here. All right. So that helps a lot. And we can identify local maxima and minima now. All right. Remember, f and f prime are continuous everywhere. There are no weird jumps in anything, okay? So we can now figure out who's who. We can draw a little picture, all right? Well, come on, graph go up, graph go down. By the way, we have a horizontal tangent line. What kind of point do we have up there? It's a local max, yeah. Okay, so I'll put L max here, L max, all right? Over here, answering part B, there is a local maximum point at, okay, x is -1. Again, folks, how do I find the y coordinate at that point? Big Daddy, plug -1 to Big Daddy. That's f of -1. Okay, f prime of -1 is 0, right? We know that. But what's that? F of -1. All right. We can work that out. If you plug it into Big Daddy f, you get positive 13. Again, I must stress, not f prime. Plug into Big Daddy f to get the actual y coordinate. We have a local max point at -1, 13. By the way, the y coordinate could be a very negative number. I mean, it's possible that you have a local max point where the y coordinate is -1 million. Why not? So don't just judge a book by its cover. All right. So -1, 13. That's the local max point. Now, what do I hear it for? Graph go down. By the way, horizontal tangent line, but we don't really care so much. Graph go up. What kind of point do we have here? Local min. All right. So we have a local, and we're applying the first dt, just using our common sense. The local midpoint at 4, f of 4, that's Big Daddy f. And that's quite negative, -112. 4, -112. So we have a local midpoint there, 4, -112. Okay. Bear in mind, we were able to locate these points here, but not in pre-calculus, right? In pre-calculus, we didn't have the ability to locate these points. Unless you have basic transformations or something. Questions? Questions? Okay. So we found the local extrema and the points at the local extrema. All right. How about the full-blown graph? Sketch the graph of Big Daddy f. Graph y equals f of x. Okay. Graph the function y equals f of x. All right. Just as a reminder, all right, f of x is 2x cubed minus 9x squared minus 24x. All right, reminder, that's f of x. Okay. What's a really easy point to find on a graph? What's the point? It's really easy to find. How about the y-intercept? How do you find a y-intercept? Yeah, okay. So f of 0, 0 is in the domain, right? Well, what is f of 0?
0.
Yeah, constant term 0. Okay, so that means that 0, 0 is the y-intercept. Okay. And by the way, it's also going to be an x-intercept.
There wasn't a 24x on the original f, though.
There was on the original f. You're thinking f prime.
Oh.
Yeah, we're back to Big Daddy. We're back to pre-calc. Okay, we're back to pre-calc. So these are some pre-calc properties, all right? Big Daddy f did have x's in all terms, all right? Now, what are harder to find? The x-intercepts. Uh-oh. And sometimes you can't find all of them. Here, we actually can, okay? Because let's look here. What do? We find the real solutions of f of x equals 0, right? So we set this equal to 0, all right? What factors out, by the way? An x, right? I'll do it right now. X, and then 2x squared minus 9x minus 24 equals 0. By the way, folks, you don't have to find the x-intercepts for graphing unless I say so. Okay, so keep track of the instructions on the test. Okay, bear in mind, I might not be asking for the x-intercepts. Okay, well this one's easy. We already know that 0, 0 is 1, right? Okay, so we know right off the bat that that 0, 0 is an x-intercept because it was the y-intercept. So we have 0, 0. Now this guy here, sadly, I cannot factor this nicely, but what's the last resort? Use the quadratic formula. Yeah. And I'm running out of space here, but by the quadratic formula, right, the opposite of b plus or minus blah, 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 blah. All right. We get about the 2 sig figs. All right. We get about -1.9, 0 6.4, comma 0. All right, so we have three x-intercepts. We have three x-intercepts. Okay, at about 0, 0, 0, and about negative 1.90 and 6.40. All right. So, ladies and gentlemen, we can do a pretty good job of graphing this thing. All right. I'm a Mac person. I don't like doing Windows, but here we're going to do Windows. What do I mean by Windows? Okay, I think this is a good way of breaking this thing down. Okay, now remember the min was way down there, so that's why it's like a cross up there. All right. Even then, it won't quite be to scale. All right. So what do I mean by Windows here? All right. In particular, I'm interested in the fence posts, right? Like the critical numbers. Okay. There are two critical numbers. One at -1. One at -1. One at +4. The intercepts I can put right on here, right? So we know that the origin is a point on the graph. Okay. We know that -1.9 is also going to be 1. And we know that 6.4 is also going to be 1. Not that I'd be all that accurate anyway, but... okay, so we know the y-intercept, we know the x-intercepts. Okay, bear in mind, we can't always find them, but we got lucky here. All right. Okay, so what do we know about this graph? We know the intercepts. By the way, this is neither even nor odd. Okay, just make my comment here. This is neither even nor odd. Although, if it is even or odd, then you can use that symmetry. That means you just need to graph one side and do an appropriate reflection of the other ones. Okay, but this is neither even nor odd, so no special symmetry. Okay, so what do we know about the graph? Well, because of the sign of f prime, we knew that the graph was going up here, right? Going down here, and going up here. All right. That's what Big Daddy F was doing. Okay. Which makes sense, because it's going to be a rising snake overall. All right. So what do we think is happening here? Oh, and also, we know the points at the critical numbers. All right. We know that -1, 13. So here's 13 over here. Okay, that's going to be a local max point. And we know that for -112, all the way down here, -112. That's going to be a local midpoint. All right. Later on, I might suggest a skeleton graph, where you kind of graph something like this, just a skeleton before we go on. Later on Wednesday, we're going to talk about what? Not just f and f prime, but also what? F double prime, the second derivative. Yeah, we're going to find that. Okay. Anyway, graph go up, right? Graph go up. Again, I'm kind of guessing here, but graph is going up, right? X-intercept, local max point. Okay. By the way, horizontal tangent lines, there are no corners of cusp here. All right. Then we're hitting the graph go down. We hit the x-intercept. The graph continues to go down. Now you might be going, okay, so when do we go from curving downward to curving upward? That's called the inflection point. That's the thing that the second derivative is going to tell us. Okay. Well, here we have kind of a no man's land, right? Big desert. All right. We'll find the inflection point later. Again, we'll find the IP later. That's where the graph changes concavity from concave down to concave up. That's what the second derivative is going to tell us. Right? Okay, down to this local midpoint. All right. Then we go back up. We go through the x-intercept. And by the way, because the multiplicities of these are both 1, we know we're going to cut through the x-axis. Okay. We shoot off like that. Cuts through. Shoot off like that. It's a rising snake overall. All right. Any questions? Any questions so far? IP means inflection point. That's for Wednesday. That's when you change concavity. Don't pack up yet. Good news, bad news. Okay, good news, we have one more example. Bad news, it's trig. Good news is, if you're clever, there's no testing. I'll explain what I mean by that. So be clever. As you've seen on the chapter 3 homework, they can pay to be clever. you might be thrilled that we have a bounded interval, but here's the bad news. I might ask you to graph the whole thing. That's the thing, on that interval. So I can have you graph on a bounded interval. All right. All right. Okay. How do we graph this thing? Okay, well, let's start by finding the derivative. Okay, f prime of x, what's the derivative? Negative sine x plus 1. You know what's a nice way to write this? Put the 1 in front. 1 minus sine of x. Okay, let's pause for a moment. All right, now I'm going to consider domain and niceness issues. F and f prime. Okay, these are nice guys. F and f prime are defined and are continuous. Okay, on this interval. Okay, remember we defined continuity on the closed interval, right? Okay. Okay, so we're good. F and f prime are good, which means the only fence posts are going to be the critical numbers. All right. So where are the critical numbers? All right. So the CNs. Let's find the CNs, the only fence posts. All right. So we want to solve. All right. Domain is all reals. The critical numbers are where f prime is what? 0. Okay, because they're not D and E anymore, right? That's always good, right? Okay. 1 minus sine of x, right? That's f prime of x, equals 0. Bottom line, add sine x, switch sides, whatever. Sine of x has to be 1, right? In order for this to hold, sine of x has to be 1. Bottom line. Sine of x has to be 1. Okay. Now, you should know your basic trig. You should know where sine of x is 1. Remember, we only care about angles between negative 2 pi and positive 2 pi. So if we take our little trek of a unit circle, okay, there's only, okay, there's one positive value between 0 and 2 pi where the sine value is 1. What's the angle? Pi over 2. That's going to be a CN. He's in the domain of Big Daddy F. Or, well, he's in the domain, this guy, right? This domain here. Also, hey, if we go this way, clockwise, there's a negative angle that corresponds to this. Negative 3 pi over 2. Okay, and these are CNs because they're in the interval from negative 2 pi to 2 pi, and there are no others. So we don't do 5 pi over 2. He's outside that interval. Right? So there are only 2 critical numbers here. Okay, these are the only values for x that make sine of x equal to 1, and they're in there. They're in our restricted domain. Okay, so the only CNs are there. Now, if we do our fence posts, those are the only 2 fence posts, what's the deal? All right, now, it's a closed interval, so I'll actually put closed dots here. Okay, here's negative 2 pi, here's positive 2 pi. It's a closed interval. Okay, that's all we care about, only those values for x. Right. We have a CN at negative 3 pi over 2. We have a CN at pi over 2. F prime is 0 here and 0 here. All right. Now you might be going, oh, bummer, do I have to test negative 11 pi over 6 or something? Do I have to test values? Actually, no, because look at this. All right. Remember, f prime of x is 1 minus sine of x. I have a question for you. Can that thing ever be negative? No, it can't. Why not? What's the most sine x can be? 1. Therefore, if you have 1 and you're subtracting something that cannot be more than 1, this cannot be negative, correct? It's 0 only at the critical numbers. So what sign does it have to be everywhere else? Positive. So it's not including the endpoints. Positive here, positive here, positive here. So what's Big Daddy F doing? Increasing, increasing, increasing. In fact, if we were to, in fact, he's going to be increasing on the whole interval. Okay. Now, I know I've given you examples where this guy's wobbled, right? This guy actually has no turning points. Okay, what does this guy look like? He doesn't wobble like some of the other guys like this I showed you. Okay, here's negative 2 pi, that's an endpoint. Here's 2 pi, that's an endpoint. By the way, this guy's even, this guy's odd, overall, neither. All right, so, and you can plug these into Big Daddy F, but if you plug this in, right, you're going to, okay, let's try this, let's try that. If you plug this in, negative 2 pi, that's going to be 1 minus 2 pi. Okay, you can plug in 2 pi, you get 1 plus 2 pi. Okay, so these points are symmetrical on the margin, right?
Professor,
Yeah.
can you explain again how cosine x is even?
Wow, okay, now that's straight.
Yeah.
So let's consider theta, all right? So here's theta, here's negative theta. The horizontal coordinate here equals the horizontal coordinate there. Cosine of negative theta equals cosine theta. Therefore, cosine is even. Okay, that's chapter 1. Okay, here's negative 3 pi over 2. Here's pi over 2. All right, graph go up. You hit this point, and you can find out where it is. Okay, graph continues to go up. Okay, and the y-intercept is 1, right? Cosine of 0 is 1 plus 0. Okay, so it's 1 over here. Okay, in fact, it goes on to this point here, right? Point on tangent line, and then it keeps going. Keeps going. All right. And then maybe we can use Newton's method to find out where this is. All right. Horizontal tangent line here. So this guy doesn't turn around everywhere. By the way, continuous on a closed interval, right? EDT applies. Absolute midpoint, absolute max point. On the interval. Right. Okay. Any questions? Yeah.
So when y is, when x is 0,